He thinks because there's we went to
Oh yeah, definitely. See, the thing about that is, won't always be free. Like traditionally, that's what's instituted a lot of states around the country, and traditionally, like after about 5 or so years, it stops application and starts getting phone to other places. And they have
Hello and welcome. This is the University of Tennessee Department of Nuclear Engineering Colloquium. I'm Art Ruggles, and today we have Wally Justice. And Wally Justice is a graduate of the University of Tennessee in 1986. He has a Bachelor of Science in Mechanical Engineering. Wally has rapidly, despite his choice of major, raised through the ranks of Tennessee Valley Authority, and he's now the chief mechanical, nuclear and codes engineer within the nuclear part of the Tennessee Valley Authority. So, Wally?
Thank you, Art. Well, good afternoon. I'm very happy to be here today at the University of Tennessee, and I do appreciate the invitation from the faculty and staff, and I hope today that I can present some information that will be of interest to some of the people that may be leaving the university in a few years relative to nuclear engineering. I also have today with me in the audience Jim Maddox, who is our Vice President of Engineering and Technical Services. So he'll be here with me today. I would like to start out and say that commercial nuclear power in the United States is really having a resurgence. Today in the United States we have 104 operating reactors that are licensed. They are running very well. These reactors and the utilities that own them have taken great strides in ensuring the safety of these plants. They have taken great strides in ensuring the generation cost of these nuclear plants. Our capacity factors for our nuclear plants have increased over the past several years. The cost of generating power has decreased over the last several years. And nuclear power is a very cost-competitive player in the energy market. Approximately 1/5 of the nation's power supply comes from operating reactors today. And as you heard, I work for the Tennessee Valley Authority, of which we have 5 operating nuclear reactors. And one of the areas that I wanted to discuss today was an option that many utilities have taken in the industry over the last several years, and that is increasing the generating output of our nuclear facilities. The Bush administration in the last year and a half has announced and has made public his support of nuclear power as part of our nation's electrical supply. The nation as a whole will need increased electrical generation capabilities to support industry and the growth of our country. One of the ways that this can be accomplished with existing nuclear facilities is by utilizing power upgrade capabilities. Now, when most of these nuclear plants were designed, particularly the boiling water reactor designs in the 60s and early 70s, there was quite a bit of design margin that was designed into these facilities. And several utilities have taken the opportunity to go in with today's analytical capabilities, computer codes that are much more capable of providing more finite answers than we had in the 60s and 70s. And we're able to go in and perform analyses to show that there is margin that can be utilized. There are capabilities in the equipment that can be utilized to allow a facility to operate at a higher reactor power level. So today, I'd like to kind of take you through a discussion of the extended power upgrade project that Tennessee Valley Authority is doing at our Browns Ferry nuclear facility. Our Browns Ferry nuclear plant is it's a 3-unit facility. It's a GE BWR-4 with Mark I containments. It's fairly early design in the BWR design phase. Right now we have units 2 and 3 are operating. Unit 1 is currently in a recovery project. for operation hopefully in the next 5 years. The plant is physically located near Athens, Alabama. And to give you an idea of how long this plant's been operating, Unit 1 came online in 1974, Unit 2 came on in 1975, and Unit 3 came on in 1977. Browns Ferry performance. One of the things that any utility that considers operating a unit for additional generating capacity, they want to see how well the unit has performed. And TVA is quite proud of the way Browns Ferry Unit 3 has performed, as well as Unit 2. Browns Ferry Unit 3 has recently completed a 669-day generation run. Unit was online for 669 continuous days. The run generated over 17.8 billion kilowatt hours of electricity. That's quite a lot of generating capability. And the refueling outage that followed this record run was 14 days and 16 hours, which was a U.S. BWR boiling water reactor and PWR pressurized water reactor record. Now, one of the things that a utility needs to do is operate safely. Another thing a utility needs to do for a nuclear facility is to operate. And we need our plants to operate reliably, and we need them to operate as often as they can. We need these plants online generating electricity. So it's very important for us to have short refueling outages, and it's very important for us to operate them in a long distance condition. Browns Ferry in Unit 3 in the year 2000 was also ranked as the third most efficient plant relative to capacity factor and generation cost in the United States. So what is a power up rate? A power up rate is an increase to either or both of the thermal or electrical output of a generating plant. Some plants have performed power up rates by installing instrumentation that measures our feed water flow through the system. They've installed instrumentation that is now much more accurate in measuring capabilities than that instrumentation was when the plants were originally designed and licensed in the late 70s or early 80s. Power up rates are also a cost-effective solution for adding additional generating capacity for future power system needs. So I believe if you look at some of the information provided by EPRI and the NEI, Nuclear Energy Institute, the nation itself needs several thousand megawatts of electrical generation capability by the year 2020. One of the ways to do that is to take an existing power plant and increase the capacity. Nuclear plants are typically licensed when they were originally designed for 40 years of operation. And in part of an extended power uprate program, you want to look at how you can extend the life of that facility. There is some conditions that you need to consider. The equipment that you're operating with, the life of that equipment. Some of you may have heard the terms life cycle management and aging equipment. Basically, most utilities will go in as part of the power uprate and ask for an additional extension to their license for the life of the plant, which is typically around 20 years. It makes good economic sense. And as part of the power uprate, major plant equipment may need to be replaced or upgraded to facilitate the increased generating capability. Part of the Browns Ferry project goals, as engineers looking at this issue, we wanted to conduct our project and look at the possibility of running our reactor at 120% of the original license requirements, the original design requirements for the facility. That would basically put us at 3,952 megawatts thermal output from the reactor. We also wanted to see what was limiting for our uprate. Now, in a power plant, there's typically 2 or 3 items that may be the limiting factor in your uprate capability. It's either the thermal capability of the reactor or the heat source. It's in the capability of the power delivering systems, your balance of plant systems, your condenser systems, or it may be in the capability of your generator, your electrical generating station. For our purposes at Browns Ferry, we found that our plant, while we could achieve 120% of the licensed power output capability, we were actually generator limited, and I'll get into a discussion of that shortly. So basically, we wanted to pick what our limiting factor was for electrical distribution, and for Browns Ferry, it was 1,280 megawatts electrical. So we're going to turn 3,952 megawatts thermal into 1,280 megawatts electrical. As part of this, we also chose to use an industry analytical tool called MelaPlus. This is an analytical tool that has allowed utilities and reactor operators to improve the core flow characteristics relative to power output. It is a more refined method that has been reviewed and approved by the regulatory authorities. And by using this analytical capability, you're now able to stretch, essentially, the operating characteristics of the reactor relative to core flow. We also chose to license and implement the alternate source term methodologies with our power uprate. Now, our source terms that are used in a nuclear facility are used for several things. They're used for aging of equipment from a radiation standpoint. They're used for dose considerations, specifically the operator dose in the control room from an accident consideration. They're also used for emission doses that are used for operation of critical equipment post-accident. And they're used for the off-site dose considerations for the general public. And each plant in the United States is licensed to a specific criteria for off-site dose. By increasing the reactor power, we had the opportunity to increase our dose consequences under the current licensing methodology. So by using the alternate source term methodology, which is Reg Guide 1.183, we were able to reduce our off-site dose considerations for the facility and meet regulatory requirements. So we will be licensing that methodology along with the power uprate. And we will also be transitioning from the current fuel vendor, which is E, to a new fuel vendor for operation for the next several cycles, which is Framatome. Framatome will be selling us fuel. Now, a little further discussion of MelaPlus. Again, it increases the maximum licensed operating boundary at the extended power output level, and essentially allows us to operate at a higher reactor power level with less core flow. We'll also recover some essential operating flexibility by restoring the operating flow range that the EPU power level will require to gain the power level we need. And there are two utilities, particular plants, Clinton and Brunswick, who are in the process of also utilizing this new MelaPlus capability, and that will be presented to the NRC prior to the submittal for the Browns Ferry nuclear plant. Brings up an interesting point. The nuclear industry, while we are all competitors, we actually work very well together in analyses and methodologies and in working in tandem with our regulatory bodies to improve the quality of nuclear power production and the generating cost and the safety of those facilities. Essentially, the MelaPlus analytical region, if you look at this original line, which is bounded in the white area here, and you look at the volume shown in red, this is the additional core operating region that we will be able to utilize. And here was our current licensing requirement of 100% reactor power. And this will allow us to operate in this region here, which corresponds to 120% reactor power. The alternate source term, as I mentioned before, is based on the methodology provided by the NRC in Reg Guide 1.183. It maintains the existing leakage limits for the nuclear facility, where we have release points to the public, and it will be again used in the control room, offsite, and mission dose calculations for the facility. And that's actually quite a large amount of work for the utility to do, the analyses to be provided to the NRC. Try the backup button here. At the same time, we are also going to be re-performing our probabilistic risk analysis for the facility. Each plant in the United States is required by the NRC to have a risk analysis for the facility. And that risk analysis determines a frequency for core damage. It also determines the value for large early release frequency, the possibility of releasing to the public. We will be redoing that PRA analysis for the Browns Ferry units with the changes for core flow, with the changes for the reactor power, and for the hardware modifications that we will have to do in anticipation of the change in the reactor power level. And we'll get into some of the hardware changes in a few moments. We anticipate very small increases in our core damage frequency, and we anticipate very little change in our reporting requirements to the NRC for our PSA. Now, this also is a major change in operating philosophy for our nuclear plant. Originally, we were only licensed to a reactor power output which did not exceed the generator output requirements. That's how we were licensed. And we operated at licensed reactor thermal power limits throughout the year. And our electrical output varied by the seasons. And the reason for that is that our generator, the cooling mechanism for our turbines is our condenser. And the condenser heat sink is a river system. And that river system operates between a temperature range of approximately 45 degrees in the winter to around 90 degrees in the summer. And so our heat rejection capabilities to this heat sink are not there or not as high as they are in the winter. Also increases our condenser back pressure requirements, and there are physical limits for our condenser that we can operate at. The new approach for us to operate is we are going to license to 120%. We're going to operate at a constant output of 1,280 megawatts. And we're going to vary the reactor power level to maintain 1,280 megawatts, which is exactly opposite of how we originally operated the plant. And there will be no major seasonal variation in total electrical output from the plant. This curve here explains basically through the seasonal river temperatures. Basically the curve here is right around 100 to 102% reactor power level, and this is 120. So in the winter we will operate at a lower reactor power level, in the summer we'll operate at a higher reactor power level. For our fuel considerations, we're going to use an average for the cycle, for our burn-up considerations. And this is a graph that shows generator capability versus our river temperature. And as you can see, I believe this temperature is around 88.6 degrees. It's where our condenser back pressure changes enough that we can no longer support 1,280 megawatts of generation from the generator. Now, part of our extended power uprate project, we had to look at, from an engineering perspective, what documents and what physical changes needed to occur in the plant to support this. And we have our design information reports, which are design bases for the plant. We had task scoping documents, which the engineers in charge of various parts of the project would determine changes that needed to be made and alternatives to existing designs. All of those were fed into task reports. System evaluations were done on the various systems. The FSAR here is our final safety analysis report, is basically our documentation back from the NRC that tells us how our plant is to be operated and designed. Our technical specification changes, which is our license requirements for physically operating the facility. Those are the manuals that the operator in the control room follows. And the power uprate safety analysis report, which is a separate report to the NRC, which will become a public document that will explain in detail the changes that we made to operate our facility at a higher reactor power level. All of this will be provided in a licensing submittal to the NRC for approval. An interesting part of our power uprate that is somewhat different than the others that have occurred in the industry is that we are doing our reactor power uprate with no change in our reactor system pressure. There is no change in the measured pressure at the reactor dome. We're doing this by increasing reactor steam flow pressure to approximately 16% above what it was originally. Our feed water flow as well will also have to increase. Part of the issues that we had to deal with from a nuclear fuel standpoint were we're going to be operating our reactor at a higher power level. How much more fuel am I going to use over an operating cycle? Browns Ferry is a 24-month operating cycle plant. Operates for 2 years. Basically believe we're going to burn 50 additional bundles each outage that will have to be replaced. We're concerned, as the industry was, about potential increased voids in the core. We will have a slight increase in the recirc pump's horsepower requirements. We're looking at that being approximately 15 horsepower. More flow means the potential for more fouling in our jet pumps. The average bundle thermal power will increase from 4.5 to 5.2 megawatts thermal per bundle. But we will operate with a flatter radial power profile. And the modifications outside of the reactor that are necessary to accommodate the 120% reactor power level is we will have some modifications to our high pressure turbine to physically carry the energy that we're getting ready to send to it. We also have reactor feed pump turbine mods that will be required. We have increased discharge pressure, the high pressure heaters. They're approaching the design limits, and there's some things we may have to do physically to those heaters to assure that they remain within code requirements. We will also need to make modifications to our DMIN system, the additional flow that will be sent through the condiments. And our balance of plant condensate system will also need increases in motors and pump requirements for the increased flow. Now, the pressure changes in the plant itself that we have predicted through analyses, we looked at a variety of reactor power levels. We looked at the original plant at 105% power up rate, at 117.5% power up rate as a sensitivity analysis, and at 120% reactor power. And reactor pressure remains fairly constant at around 1,050. Our high pressure turbine inlet pressure actually decreases slightly at the 120% reactor power case, and it's based on the amount of flow that we're sending through the component at the time. Other components, moisture separator discharge as part of the balance of plant will increase slightly, but as you can see, the physical changes to the plant itself from a pressure standpoint are actually fairly minimal. We will also be increasing the amount of heat we place into the physical plant. Our heat rate for the facility will increase from the original value of approximately 10,000 BTUs per kilowatt hour to 10,500, somewhere in that range. So we have more heat running through the facility And engineering as a whole had to go and evaluate all the components associated with the physical plant to assure that this heat rate was acceptable. Now, originally I said there were some design margins in these plant designs from the late 60s and early 70s that allowed us to increase the reactor operating limits. There are also some design margins that are in our balance of plant systems for the most part. However, we have found there are some components that were limiting from the original design, and those are the modifications that I just previously showed you that will be required to make this modification acceptable. Now, we have found that we are a generator-limited facility now if we make this power uprate. And what I mean by that is the generator, the electrical generator physically can carry no more through it. It cannot operate at any level greater than 1,280 megawatts. Our plan again is to operate at a constant power profile of 1,280 megawatts. And we should be able to do that based on the way our system's operated. Although the electrical transmission system does have some resistance in it. And that resistance changes fairly rapidly, and it changes often. And that is measured in megavars. And generating facilities have to operate their systems to coincide with the frequencies needed for the transmission system. And basically, we believe that Browns Ferry will probably operate around the system resistance of 100 megavars. And so we will be somewhere between 1265 and 1280 megawatts during our normal operation. We also have some additional modifications that we will need to make. We're going to be increasing our hydrogen pressure to 75 pounds in our generator system. The comment on derating our generator during the 18 days under worst summer conditions, if we look at our meteorological profiles for our facility, if you remember back to the curve I showed you for power output versus river temperature, anytime we get above 88.6 degrees Fahrenheit in our heat sink, our generating capability will go down due to the back pressure requirements in the condenser. We predict those to be on average around 18 days for each year. Those are the hottest days in the summer. We also, I apologize for this. Does this move?
Move the slide. Yeah.
Okay.
You click on the top part
Push
of
and drag it down.
it.
Drag it down.
Yeah. You have to.
You can do it with your finger.
You do it with your fingers.
There you go.
There we go. We also have to go in and evaluate the physical supports of the generator system because of the increased energy we're going to be putting through the system. So from an electrical engineering standpoint, there's quite a bit of work that had to be done. Part of the efforts that were done in early extended power uprates were done at Plant Hatch and the Monticello plants. Those are also BWRs. And General Electric developed a lot of the methodologies that we used to go in and perform our evaluations. We're also, as I mentioned before, looking at a constant pressure power uprate evaluation, which is where we wanted to maintain our reactor pressure constant. We did not want to increase that. We will be the lead plant for that evaluation, and that will be submitted to the NRC as part of our update package. Now, being the lead plant means that we, as a utility, will probably get the majority of questions from the regulator on this issue. It's noted in here as RAIs. Those are requests for additional information. So when we submit a licensing change request to the regulator, their methodology of coming back to us and asking clarification questions or other information is through a request for additional information. We met with the NRC on December 5th of 2001, and we agreed on the schedule with the NRC for continuing with our uprate project. And our goal is to have zero requests for additional information. We want to have as much communication with the regulator, and we want to have as good a quality of documentation as we can to ensure that we have done the correct work, technically correct work, for this project. Now, some of the project issues that I've touched on in some places earlier in the presentation, our high pressure turbine pressure increase is approaching the design limits on the high pressure heater shells. And so from an engineering perspective, we have to go in and do component analyses to determine the effects of that. Those are underway. Our research system vibration, that has been an industry issue for power uprates. It was noted by us as a potential issue, and we are studying that phenomenon due to the increased flow. Additional pump modifications that may not have been considered as part of the original project on our feed pump, condensate, and condensate booster pumps on our balance of plant. And of course, we will be the lead plant for the constant pressure power uprate methodology. So those are some of the issues that we have in this large project to deal with as engineers. Benefits. Now that I've said all of this, what are the benefits of a power uprate? Well, our previous generator output was 1,163 megawatts electrical. And that is when conditions are ideal. Our generator output varied with river temperature, which based on a higher temperature, we would basically produce around 1,138 megawatts electrical. And at a lower river temperature, we would get to our maximum electrical output of 1,163 megawatts electrical. Now, our new generator output, because we wanted to have a flat generation profile, will be 1,280 megawatts or slightly less depending on the system resistance of the transmission system. So, bottom line, for a 24-month operating cycle, we anticipate gaining an additional 2 million megawatt hours with each of our nuclear units at the facility. Now, when you look at that, at a 3-unit site, if all 3 units were running, that's almost another small nuclear unit that you've gotten with your existing equipment. You've had to perform analyses, a lot of engineering work. You've had to go through a licensing process with your regulator, and you've had to make some physical hardware changes. But the benefits of doing a power uprate on an existing facility far outweigh going and building a new facility. And the facility you may choose to build as a utility may not be a nuclear facility. More than likely, it will be a coal-fired or a combustion gas turbine. So these power uprates are a good way to further the capabilities of the nuclear power plants that were designed. Now, these large power uprates are being done on boiling water reactors because just by their design, they had additional margins that you're able to use. By their reactor design, it's easier to perform flow modifications. The pressurized water reactors in the United States, for the most part, have all done power uprates relative to the feed water systems, the instrumentation used to measure feed water flow. And that has been a common update and has gotten most of those utilities and most of those plants between 1 to 1.25% equivalent reactor power increase, which basically is around 5 to 7 megawatts per unit. So, again, for no cost in fuel, doing some engineering analyses, being innovative, looking at new technologies available, we're able to get more out of existing facilities. Now I'd like to move on to another topic that's near and dear to anybody that has worked in a pressurized water reactor, and that is steam generator replacements. Steam generators are the Achilles heel of PWRs. When PWRs were originally designed, especially PWRs with U-tube steam generators, U-tube heat exchangers, The industry did not understand the effects of chemical additions to plants. They did not understand completely the metallurgical effects of temperature and flow requirements. There were also some inherent design problems with certain model steam generators where there was vibration in the tubes that fretted against components internal to the steam generator. Basically, a steam generator for a PWR is licensed only to allow you to plug, due to defects, up to 15% of the tubes in that generator. And once you have reached that limit, you have exceeded your analysis capability for your plant and your license requirements. And the decision to replace a steam generator due to failure phenomena is a very crucial decision for a utility. Several utilities have made the decision not to replace a steam generator in a unit. You have plants that were designed for 40 years of operation that may have only operated 10 or 12 years, have steam generator problems, and it's not cost effective to replace those generators to continue operating the unit. Therefore, a nuclear plant does not continue to operate, one less in the United States or in the world. For other utilities, it makes sense to go in from an economic standpoint and replace these components with new designs that will meet the requirements of operating for the remainder of the plant life. And in most cases, most utilities will go in and ask for an additional extension of a plant life for 20 years. So now you're operating a facility for up to 60 years. The industry as a whole has done a very good job of understanding the failure phenomena in steam generators due to the industry issues. They have also done a good job in working with vendors in making design changes such that a steam generator replacement is actually feasible. Now the picture you have in front of you, if I can get this up here, this is a steam generator. This is actually the Sequoia steam generator, which we are going to physically install in March of this year, March of 2003. And that piece of equipment there weighs 340 tons. So it's a fairly large piece of equipment. There are 4 steam generators in the Sequoia nuclear plant. It is a 4-loop PWR. You can see the other 2 of the others in the background. That picture was taken in Korea, where they were manufactured approximately a week ago, and they are now loaded on a ship and on their way to the United States to be offloaded at the Sequoia site. We talked about pressurized water reactors having water chemistry-induced failure mechanisms in tubes of steam generators. And we talked about the fact that, as with extended power uprates, if you're going to spend the money for a steam generator replacement, which is a very large project, you want to typically go in with a plant life extension to make it cost beneficial for the utility. Now, to give you an idea of the amount of work that is required in determining how to replace a steam generator in the plant, or all the steam generators, TVA has worked on this for approximately 3.5 years with a fairly large team of people, engineers, determining what physically needed to be designed for the new steam generator. How would we physically get the old ones out and the new ones in? Again, they're 340-ton components, and they sit right next to a reactor core with fuel in it. So we have to have some way of handling that. Sequoia will replace these 4 steam generators in March of 2003, and to accommodate the increase in the steam pressure and some other issues we had with an aging high-pressure turbine, we're also going to replace our high-pressure turbine at the same time. We made this decision based on the future predicted tube failure rate that we had in our existing generators. Gives us an opportunity to recover our secondary side steam pressure, which will increase the efficiency of the plant. Our plant, over its operating period, which Sequoia started in 1980 on Unit 1, has lost about 32 pounds of secondary side pressure due to basically corrosion, plating out, and the secondary side components. And plugging of steam generator tubes as they failed. And when we're done, we believe that Sequoia will increase its output by about 20 megawatts for the high pressure turbine and the steam generator replacement. So again, it's an opportunity for us to increase the output of the plant and increase the life of the existing facility. The steam generator replacement at Sequoia will require approximately 70 days for removal of the existing steam generators and replacement and installation of the new generators. And I mentioned before that it's an engineering feat in a way of trying to go into a containment for a nuclear power plant, cut an opening in that containment, physically remove the old ones and install the new ones right around a reactor core full of fuel. And we aren't the first ones to have done this by any stretch of the imagination. There have been several steam generator replacements up till now. But there is a lot of safety considerations for the nuclear fuel when we're trying to handle equipment of this size. We're going to utilize one of the largest cranes in the world to handle these steam generators. I'll show you a graphic of that steam generator in a moment. And we will be housing our original steam generators, which are radioactively hot and contaminated, at our site for the remaining life of the facility. That is our plan at this time, in a mausoleum that we have specifically constructed for storing these four components. The engineering work that went into the steam generator replacement project was dealing with the increased heat transfer area that we were going to get out of our new steam generators. They're actually slightly bigger, they're more efficient. We had to review the effects on all of our plant systems. We had to understand, by having increased secondary side pressure, what did that do to components that had been in service for 20 years. Our accident analyses, which are our license requirements by the NRC, we have to have a set of accident analyses formed to look at how a plant responds, how the design responds, and any dose considerations for a loss of coolant accident, steam generator tube rupture, a main steam line break. All nuclear plants have to have these analyses done. These were reviewed for design margin associated with the steam generator replacement. And then, of course, we have the physical transport and construction issues that I have mentioned. Now, the steam generator you saw earlier in the picture, this is a fairly accurate two-scale drawing of the steam generator relative to the crane. So it is a fairly large crane. The crane itself right now is in South America on a job. There's only 2 of them in the world. It takes, if you were to ship it by truck, it would take 160 tractor trailers to physically move the components of this crane. It takes us 6 weeks to build it. We've actually built a fairly large concrete base pad for this crane to physically sit on. So it is a large piece of equipment. And our plan is to basically open up the top of our containment, reach down in, pick the old one up, set the new one in. That's as simply as I can put it. But it will be interesting to see this crane in operation when this actually occurs. Again, just kind of a physical size comparison. That's one of our steam generators being loaded in the ship's hold last week. And there are all 4 of them at night with the lights on, being ready to be shipped off. A lot of years of work on this project. To see them in a ship is good. To see them on their way, finally built. Does anybody have any questions relative to either of the topics that I've talked about or anything else? Yes.
How have the steam generators generally been replaced? Have they not gone into the side of the containment?
Yes. Most facilities have utilized their equipment hatch. A lot of plants have an equipment hatch that physically opens to the outside environment. Unfortunately, the Sequoia plant has an equipment hatch that opens internal to the plant, and it is right next to our fuel storage pool. There were some issues that we had to decide how to deal with as far as safety. How do you move a 340-ton component over nuclear fuel, spent nuclear fuel? We decided that the best choice for us was to physically open up our containment and do a direct lift out for those safety considerations. Yes?
Will the Corps have used fuel in it at the time?
Part of the time it will, yes, when these activities are going on.
I have another question.
Yes?
The curve that you showed on the Browns Ferry energy production as a function of time during the year, you had more of your power output in the summer. The curve seemed to go up and back down. You were generating more in the summer and less in winter. Well, as you said, there's more capacity, potential capacity in the winter because of the lower temperature of the cooling water. I wonder why you did it that way.
Can I get back to that slide and I'll...
Yeah.
Which one is it? Keep going down.
Lower temperature. It's got
Back right there, yes. No.
A couple before that one.
There we go.
That's it, yeah.
Thank you. Actually, what this is showing is it is showing that we're going to maintain a constant generator output of 1,280 megawatts. We'll be able to maintain 1,280 megawatts in the wintertime when the temperature is lower in the river at about 100 and 101% reactor power. It'll take us 120% reactor power to generate that same amount due to the increase in the heat sink.
I showed it at the bottom.
And so that's the temperature range is like 65 to 90?
It's about 45 degrees
45.
to 90, somewhere in that general area. Yes, sir, Dr. Dodds.
You mentioned changing the fuel supplier for Browns Ferry from General Electric to Framatome.
Yes.
Why?
Those are just business decisions. They're contractual decisions on what fuel is offered and at what price and how will that fuel perform. It's not uncommon for nuclear utilities to change fuel vendors. Framatome's actually doing quite well in the fuel business at this time.
Is that Will's back out in Wilcox?
Yes. Yes, sir.
Behind the feed water system, what is the next limiting component in upgrading a PWR?
Behind the feed water system, we have, for us it would be back to the generator capability. If you're looking at the physical plant, for us, I would have to say it's in the condensate pumps. If we're looking total plant, I would have to say that our electrical generation capabilities would be the next most limited.
What was the major deterioration in the steam generators that caused you to make the decision that, was it the denting, was it the thinning, cracking of the support plates? What kind of failure mechanisms did you have there?
Actually, it's a combination of all over the years. Denting occurred early on. The thinning of the tubes or the stress corrosion cracking in the tubes has occurred due to just the age of the metallurgical properties of the material. We have, since operation of the plant, monitored and know which tubes have problems through eddy current testing and other types of testing.
What percentage of tubes did you have plugged?
I believe we were at Sequoia. I believe we were around 8% in one generator. We were not at the limit by any stretch of the imagination. However, it made the best business sense to go ahead and order our generators at the time that we did, which was approximately 4 years ago, because it's hard to predict the future on failure on equipment. You have to almost look at the worst case, and that's what we have done.
Is there any difference at Watts Bar?
I'm sorry?
Is there any difference in the Watts Bar plant?
The Watts Bar generators are a different model generator. We're currently looking at the life of those generators and when they will need to have a replacement performed.
They were actually planning a replacement, I think, in cycle 7. Actually, it'll be quicker than one at Sequoia. They're a preheater type steam generator that a Model D Westinghouse has really pretty much had the worst industry performance. It was the next generation from the Sequoia type, but it did not work out.
All right, well, let's take one more question, and then we'll adjourn to our refreshments downstairs.
When you restart Unit 1, is that going to be with the original power, or are you going to include the power upgrade?
We plan to do a power upgrade with that project as well.
Is there any problem with restarting it under the new system or under the new technical specifications at all? Or?
No, we do not believe so. We'll actually have an opportunity to increase that unit's output more by rewinding the generator as part of the upgrade project. I think we'll be around 1,340 megawatts, I believe.
Okay, you're invited to ask additional questions or converse with Wally downstairs. We have refreshments downstairs after our colloquia, and everyone, including the non-nuclear engineers, are invited to come down and mingle with us there. I think that when I met Wally in Muscle Shoals, he confided with me that he ascended through the ranks partly as a result of attrition and the demographics of the TVA engineering staff. I think that's probably just a very small part of the reason that he's here, but I understand he has some handicap as a result of a decision he made when he was young, and we all make mistakes when we're young. And I want to help Wally to continue rapidly onward with your career. And so what I have for you is this pseudo nuclear engineering degree. I wish I'd make it honorary, but they won't let me do that here. And what it says basically is, had you made the right decision when you were younger, you could have been a nuclear engineer. I feel certain.
I could have.
By virtue. Thank you. By virtue.
Thank you.
Frame that for you, bud. Put it on the wall.
Also has some things to something out here.
Screw the railgun. I'm building the crane.
Are we off the thing now? I have some pamphlets on TVA if anybody's interested. And some TVA pens. Freebies.
We're in college. I'll take it.